Beneath our feet, Earth is constantly erasing its own history. The planet's interior is a churning engine of tectonic plates, continuously melting and recycling the crust, which swallows up the physical evidence of how our world originally formed. Mars, on the other hand, is a quiet world. Its geological activity slowed to a near halt roughly 3 to 4 billion years ago, leaving the planet's interior frozen in time as a preserved relic of the early solar system. To read that history, NASA deployed the InSight lander in 2018. Unlike rovers that roam the surface, InSight's mission was to sit perfectly still on the Martian equator, wait and listen. It was equipped with a seismometer so sensitive it could detect ground movements smaller than the width of a single hydrogen atom. By recording hundreds of subtle Marsquakes, the lander began to map the planet's internal structure. The data returned from the red dust gives us a direct view into a primordial state, allowing us to study the exact physical processes that shape rocky planets before tectonic recycling wipes the slate clean. What InSight's seismic waves revealed was a mantle that is highly irregular. Instead of a uniform layer of rock, the interior is lumpy, filled with dense anomalies that shift the speed and direction of the waves. These lumps are the shattered debris of ancient massive impacts. Billions of years ago, asteroids and protoplanets smashed into the young Mars, driving fragments deep into vast oceans of magma that eventually cooled, locking the foreign rock in place. Because Mars has only about 1/10 the mass of Earth, it couldn't hold on to the heat from those ancient collisions. The planet cooled quickly, and the internal churning that drives geological activity ground to a halt. Without that churning core, the planet's magnetic dynamo failed, the protective magnetic shield collapsed, and the atmosphere was left exposed to solar winds, which slowly stripped the air away into space. The rapid cooling that preserved the planet's early geological history also doomed its surface, transforming Mars into an irradiated, arid wasteland. Today, the Martian atmosphere is less than 1% as dense as Earth's. It is too thin to trap heat, meaning a person standing on the equator at noon might experience room temperature at their feet, but freezing temperatures at their head. These sharp temperature gradients generate winds that drag across the surface in a process called saltation. Gusts lift heavier sand grains that bounce along the ground, and those physical impacts knock fine, electrostatically sticky dust high into the air. Once airborne, those dust particles act like tiny radiators, absorbing heat from the sun and warming the thin air around them. This warm air rises, drawing in even more wind from the sides, which in turn kicks up more dust. Left unchecked, this thermal feedback loop scales rapidly. Regional weather systems merge until they form continent-sized superstorms, thick, choking walls of dust that can blot out the sun across the entire planet for months at a time. This thin atmosphere fails to protect the surface, creating extreme thermal instability and megastorms that force anyone on the ground to contend with a permanent survival hurdle. We have already seen the lethal potential of these storms through the fate of our own machines, specifically the Spirit and Opportunity rovers. As the fine, sticky Martian dust falls out of the sky, it coats the flat solar arrays. Because the dust is electrostatically charged, it clings tightly to the panels, steadily cutting off the rovers from their only source of energy. During the global dust storm of 2018, the atmosphere became so saturated with dust that it blocked 99% of incoming sunlight. With its panels swamped and power generation dropping to near zero, Opportunity was forced into an emergency hibernation. A solar-powered rover cannot survive long without electricity. Once the batteries run completely flat, the onboard heaters shut down. Plunged into -75-degree Martian nights, the extreme cold causes sensitive internal components to permanently break. The weather on Mars actively hunts and destroys solar technology. For human settlers to survive here, they will require power sources that do not rely on a clear sky. To escape the lethal combination of solar radiation and planetary dust storms, future colonists will need to move underground. Ancient, empty lava tubes left over from Mars's volcanic past offer deep, natural shelters. Finding and mapping these subterranean caves is difficult. Because of the vast distance between Earth and Mars, communication signals face a delay of up to 22 minutes, making real-time remote control of a scouting rover impossible. Engineers are turning to a different kind of mobility. Robots like Boston Dynamics Spot use legs instead of wheels, allowing them to step over boulders and navigate the steep, uneven floors of a cave where traditional rovers would get stuck. Equipped with advanced AI, these legged robots operate entirely on their own. They can walk into a pitch-black lava tube, build a 3D map of the terrain using onboard cameras, and independently identify points of scientific interest. Establishing a foothold on Mars means cutting the communications umbilical cord to Earth and relying entirely on autonomous machines to secure our shelters. Once a secure location is mapped, those same autonomous systems will lay the groundwork for human habitats. Specialized robots will excavate the local Martian regolith, mix it with extracted water ice, and 3D print the habitat structures layer by layer. To further protect colonists from cosmic rays passing through the thin atmosphere, machines will shovel thick layers of that loose regolith directly over the printed habitats, creating a dense physical barrier against the radiation. Inside the base, survival comes down to chemistry. The Martian soil is laced with toxic salts, called perchlorates. But by washing the dirt and utilizing specialized bacteria, colonists can safely separate out liquid water and generate breathable oxygen. To keep all these life support systems running through a months-long dust storm, the settlement will rely on a hybrid grid. Compact nuclear reactors will provide the baseline heat and electricity when the solar arrays are buried in the dark. The rapid cooling of Mars's core billions of years ago left behind a beautiful, broken world. Establishing a permanent home there will force us to push the limits of automation, engineering, and our own endurance.